Okay, let's get straight into it. Mastering 13.1 cyclic photophosphorylation, specifically the part involving photosystem I and ATP synthesis, is absolutely essential for your Cambridge Biology 9700 success. And I'm really not exaggerating here. This specific topic shows up in literally every single examination series. It's guaranteed. But if you don't know exactly what the examiners are looking for, well, you're just leaving guaranteed marks on the table. So today, we're going to expose exactly how to secure those marks.
Now, I want you to listen to this phrase really carefully. Electrons are excited and make ATP for the plant to use in reactions. You know, Cambridge exams are incredibly stressful. And when students see a multi-step biological pathway question, it's super common to just panic. And so they write something exactly like this generic sentence. I mean, it sounds like biology, right? It's got the word electrons, it has ATP, but in a high-stakes exam setting, this answer is a complete trap. It's a deeply flawed, super generic response that consistently loses marks.
And actually, when I say it loses marks, I literally mean it earns exactly 0. Nothing. Nada. You see, ordinary revision and just basic rote memorization, they completely fail when we're dealing with complex biological pathways. You literally can't just parrot back a simplified summary and expect a pass. The Cambridge syllabus makes it crystal clear. Top-performing students have to exhibit a connected conceptual understanding, and they need to be able to transfer that to totally unfamiliar contexts. If you just memorize basic phrases without grasping the underlying mechanics of how it actually works, you are definitely going to score a 0. Okay, let's dive into this. We need to lock down the core theoretical principles first. So, cyclic photophosphorylation is a light-dependent process. And notice the specificity here. It involves only photosystem 1, or PSI. In this process, excited electrons cycle through an electron transport chain for the express purpose of synthesizing ATP, before those exact same electrons return right back to PSI. The cycle is completely closed, hence the name, right? Cyclic. It's kind of like a water wheel, where the water is pumped right back to the top to be used all over again. The causal relationships here are incredibly precise, and your definition needs to be just as precise. Let's map out this logical sequence step by step. It all kicks off when light energy hits PSI, and that excites the electrons. This excitement literally forces those electrons to enter the electron transport chain, which creates the exact conditions needed for ATP to be synthesized. And finally, the cycle completes as the electrons return home to PSI. So why do students find these multi-step pathways so tough? Usually it's because they miss this unbroken narrative. Examiners want to see systematic analysis, you know? They want to see that you understand how that initial excitement physically causes the chain reaction. This is exactly how top-performing students demonstrate mastery. They present the sequence as a fluid, logical chain of evidence-based reasoning. To really understand what goes wrong for most people, we dug deep into the Cambridge Principal Examiner reports. And here are the top 3 examiner warnings for this specific topic. First up, examiners note that students constantly confuse cause and effect in the pathway. Second, students just forget to check their units and use correct scientific terminology. And third, this is the absolute classic mistake, providing generic answers that just aren't specific to the context given in the stimulus material. The reports highlight over and over that candidates who reference cross-topic connections and apply specific contextual reasoning achieve significantly higher marks. So let's look at how this builds into your overall exam strategy. We're talking about something called the method mark strategy, and it is a total game changer. In complex problems, marks are very often awarded for the process itself. This means systematic processing is your absolute best friend. Examiners are actively looking for a standardized sequence, identifying key elements, applying relevant principles, executing analysis with clear working, verifying results, and then presenting them in the appropriate format. If you show the method, that systematic sequence of analytical reasoning, you can secure marks even if your final conclusion ends up getting slightly tingled. But here is a really critical question for you to consider, and it's honestly a bit of an insider secret. What is the single examiner clue that completely changes how you must structure your answer? In just a moment, I'm going to share the exact clue you need to look for that completely transforms your approach. But first, you need the foundational framework that makes that clue utterly obvious when you finally see it. So the crucial point is mastering the ultimate examiner framework. To truly conquer these harder application questions, you absolutely need a structured approach to analyze and evaluate. Here is that step-by-step deconstruct, solve, evaluate framework. Step 1, anchor yourself in the concept. Identify the core biological principles at play. From there, step 2, pull the evidence or data directly from the stimulus materials provided. Next up, step 3, apply scientific reasoning to systematically solve the problem, check if it's reasonable, and justify your decisions using that evidence. And finally, step 4, package the whole thing with the correct examiner wording. You've got to present your findings using precise terminology and comparative connectives. It's essentially a descriptive, analytical, and evaluative ladder that guides you safely right to full marks. Now, part of that evaluative framework very often involves statistical analysis, especially when practical experimental skills are being tested right alongside theory. You absolutely must map exactly when to use which test based on the stimulus materials. For instance, if you are comparing means, your go-to is always a t-test. Dealing with categorical data, that's going to be chi-squared. And if you're hunting for relationships between variables, well, you rely on correlation tests. Top-scoring candidates constantly demonstrate this kind of evaluative thinking by selecting the appropriate analytical framework and, crucially, justifying it. All right, let's actively escalate the stakes here and put your schools to the test with a quick scenario. Imagine reading this. Electrons from PSI enter the chain to make ATP. The t-test confirms ATP increases. I want you to pause and predict right now. Spot the errors. Think about our framework. Think about those examiner warnings. Okay, first up, make ATP is just really poor terminology. ATP is synthesized. Second, saying they enter the chain to make ATP completely skips the causal step of the electron transport chain, generating the necessary conditions for that synthesis. And finally, using a t-test to simply confirm an increase over time, that is a total misapplication of statistical analysis. A t-test compares means between two distinct groups, not just a simple directional relationship of a single variable. And this brilliantly illustrates the vast canyon between a generic student answer and a true top-band examiner answer. The flawed approach completely fails because it doesn't link to the specific scenario, it uses really loose phrasing, and it just skips over major logical steps. On the flip side, the winning approach succeeds because it purposefully deconstructs the question, uses precise terminology like synthesize, applies the correct statistical framework, and justifies every single connection with evidence from the stimulus. It literally leaves zero room for the examiner to doubt your conceptual understanding. So let's quickly recap the 3 key exam-focused takeaways for tackling cyclic photophosphorylation using this framework. Number 1, deconstruct the question carefully. You need to know whether you're dealing with knowledge, data handling, or experimental skills. Number 2, extract relevant data directly from the stimulus. Please don't just write from memory alone, use the actual evidence provided to you. And number 3, and honestly this is the most crucial point to remember, link every single point to the specific context given. Whether it's some unfamiliar plant species or a totally unique experimental setup, your answer absolutely must be grounded in their specific scenario. But here is the ultimate diagnostic cliffhanger I want to leave you with today. Imagine you're sitting there in the exam hall. You applied the framework perfectly. You mapped the cyclic pathway of PSI flawlessly. You checked all of your terminology. But then you get your paper back, and you still lost the mark. Why? How is that even possible? Well, the hidden cause actually lies in one specific word that was hiding in the question itself. A single clue that completely dictated the mark band. That hidden cause? It's all about command words, the precise verbs examiners use that essentially decide your fate. To solve this exact cliffhanger and ensure you never, ever lose a mark to a misunderstood command word, make sure to subscribe to Ace the Exams to excel in your Cambridge examinations. Our next explainer on command word awareness is your mandatory next step to locking in those top grades. So, practice those past paper questions, apply the framework, and I will see you in the next explainer to crack the code on command words. Keep analyzing, keep evaluating, and never stop questioning the data.